I want to apologize. I don't know if you could see after I reviewed that video, I don't know if you could see the window in my calculator as well as I thought you could. So if you couldn't see it, I was describing the keystrokes, so you should be able to handle that. But I want to review again some of these steps to start this video. So again, I also made a mistake on the last video, the derivation, or how I showed you how you go from pH to concentration of the hydrogen ions. So I wrote it out correctly here. I had a negative sign written here and here, and I shouldn't have. But they canceled out, but it probably was a little confusing or misleading to you. But again, to go from a pH to here, I'm showing you here the steps. So you don't have to do all this. I'm just showing you where it comes from. But you plug in the pH into the definition. 1.60 equals the negative log of the hydrogen ion concentration. Then I moved the negative sign to the other side. And then I took the inverse log of both sides. And that cancels this. So you're left with just the H plus, our unknown variable, if you will. And when you take the inverse natural log, or inverse log, I'm sorry, base 10 of a number, it's the same thing as raising it to the power of 10. So this is exactly the same as 10 to the negative 1.6. So again, let me show you. I think this will be, I can see on my camera that it's even better. So I'm hoping it was visible in the last video, but in case it wasn't, this is again how you do that. To do this in my particular calculator, all I have to do is enter the number 1.60, the negative of it, and press second LOG, and you'll see I do get that 0.025 and with a bunch of other digits, but I have to round it off at the third decimal place. That's where that 0.025 comes from for the concentration of the hydrogen ions. And then I went into talking about calculating these other ones, and I think that was pretty clear on the last video. And then what I was talking about was this slide here of where does that pH of 14, or where does that scale between 0 and 14 on the pH scale come from? So I ended the last video showing you this slide here where we were talking about the auto-ionization of water. Reacts with itself. It's got a very small value of K, which we write like this. It's the products over the reactants, but the reactants have a constant value. We don't include them. It's really just the number 1, so we don't include it, and it has this value. If you take the square root of since these are equal, it's really saying take the square root of that number and you get the solution, you get the value of each of those. If you multiply 1 to the negative 7th by itself, you get 1 to the negative 14th power. And what does that mean? It means that in any solution, in any aqueous solution, this will always be true. So if you know one of them, you can calculate the other. So if you add protons to water, the equilibrium shifts to the left. Okay, if you add protons, it shifts left, which means that that goes up, but that goes down. If you add hydroxide ions to water, this goes up, so the equilibrium shifts that way, so that goes down. But they balance each other out. If the proton concentration goes up, the hydroxide drops. If the hydroxide ion concentration increases, the proton concentration drops. But they always maintain that constant product of 1 to the negative 14th power. So to summarize what this all means, that you can look at the molarity. Remember, these brackets mean moles per liter. So it's molarity. If that is greater than 10 to the negative 7th, which is really half this number, you have an acidic solution. If it's less than 10 to the negative 7th, you have, that would be the concentration of the hydroxide ions. Neutral solution, pure water, distilled water, would have them equal. And a basic solution has the concentration of the hydroxide ions being the dominant part of the solution. I think what I'd like to do now is just give you a little more practice with this, converting between pH and concentration. So as I had on the slide or in the last video showing you how you go from here to here or vice versa. Let's just do a few more examples. Let's make up some numbers here. pH calculations, we'll call them. And make sure you have your calculator handy here while you watch this video. Let's just say I give you a pH. Let's start off easy, a pH of 2. What does that mean for the concentration of hydrogen ions? Well, you again, in your calculator, would enter it simply like this. You take the pH of 2, type it in, but you take the opposite of it, enter -2, and then press second log, and you see 0.01, which is the same thing as saying 1 times 10 to the -2 moles per liter. So you can see the pH, when it's an integer value, becomes the negative power of 10. So a pH of 3 means the hydrogen ion concentration, you might have guessed, would be 1 times 10 to the -3 moles per liter. If you don't believe me, type it in, 3 negative, second log, you get 0.001, which in scientific notation is 1 times 10 to the -3 power. So you can write it either way. Either way is fine. What if you get some odd value? Let's just say it's pH of 8.27, some random number like that. What is the concentration of H plus? Again, that's equal to 10 to the -8.27 power. So I'll enter that in. Let me go back to regular mode. I have 8.27 negative second log. It should be a number that's a little bit less than the 10 to the -7th, because that's halfway. It's 5.4. I'd round it to 5.4 times 10 to the -9th moles per liter. So you can see this pH represents a solution that is slightly basic, which means that the concentration of protons should be less than 10 to the -7th, which it is. This is a smaller number. That number is less than 1 times 10 to the -7th. It's hard to think on these very small numbers, but that's a true statement. And if you're not sure if you did it right, all you have to do is go back to the solution. So enter in 5.4 EE -9, enter that in like that, and just press the logarithm of that number, and then take the opposite of that number, and you see you have 8.27. So you did it right. All those digits you got to throw out. This concentration has 2 significant figures, so you have to include only 2 decimal places in your answer. You'd have to round it to 8.27. If the concentration, you probably are getting it by now, let's say it's 1 times 10 to the -13th molar. That's a pH of 13. Just go in 1 EE13 minus log, you get -13, but you got to take the opposite of that because pH is the negative logarithm, so it's pH of 13. So it works out. So again, make sure you can do that on your calculator, even not just nice whole numbers, round numbers, whatever you want to call them like that, but any realistic random number like that as well. Let's see here. I want to put this back up just to stress how important this is. So notice again that in whether you're an acidic, neutral, or basic, there is a very important relationship between the proton concentration and the hydroxide concentration. Since they both multiply to this number, there you go, then they will always have this relationship. If you're an acidic solution less than pH 7, the protons will outnumber the hydroxide concentration. They'll be larger. These will be larger than those, this number. Neutral water, they're exactly equal. And in a basic solution above pH 7, the hydroxide ion concentration will be larger than the proton concentration, but they always will multiply to give you that number. That is the key to the whole thing. So now let's just go and do a little bit of, since I think some of you might be a little lost with the logarithms, it's been a while. Let me just show you where they come from. So again, the pH scale was invented because proton and hydroxide ion concentrations are really small for most dilute acid and base solutions. So here's a review of what logarithms are. So the LOG, the word LOG means you're in the base 10. You'll sometimes see written in math books like this with a subscript 10. So the log of 100 base 10 is 2 because the base raised to the second power is 100. 10 times 10 is 100. The log of 1 is 0 because any number to the 0 power is always 1. The log of this small number, 0.001, is negative 3. Why is that? Because I can write this number, 0.001, as this, 10 to the negative 3. And I can also write it as 1 over 10 to the positive 3. So a power of 10 becomes positive. Negative becomes positive when you flip it, when you put it in the denominator. Well, that number here is just 1 over 1,000. And the logarithm of that number is, yes, 1 over 1,000, so 0.001. Yeah, I was trying to show you why that is equal to that. So 0.001 is the inverse log of negative 3. Lost my train of thought there for a second. So the other thing is with deriving this formula, where the number 14 comes from, is this let's go back to the equilibrium of water. Now I can write the auto-ionization of water like this, a little simpler. How did I have it written before? I had it written like this: 2 water molecules giving you H3O plus and OH minus. But I can write that in a simpler way like this. I just write 1 water dissociating to give you a proton. Hydronium ion and the proton are the same thing, plus an OH. So this is just a simpler version of that more complicated equilibrium expression. So if I write the Kw of that, it's equal to the concentration of protons times the concentration of hydroxides. We know it's equal to 1 to the negative 14th. Well, what if you take this expression and just take the negative log of both sides? All right, I can do that. It means I haven't changed the equation. It's still equal to itself. I've done the same thing to both sides. And the property of logarithms, a special property, is when you take the logarithm of a product, 2 numbers multiplied by themselves, it's the same thing as adding the logarithms up. So the negative logarithm of this product is the same as the negative log of this part plus the negative log of this. And the negative logarithm of this number is just the power 14. This is the definition of pH, negative log of H plus. This is the definition of what's called pOH. It's just a different way of expressing the acidity or basicity of a solution. But they add up to 14. So this is why the pH scale goes from 0 to 14. If, for instance, the pH is equal to 2, it means the pOH is 12. If the pH is high, that would be an acidic solution. If the pH is really high, let's say it's 10, the pOH is 4. That's a basic solution. They always add up to exactly 14. Most people don't use pOH. It's more common to use pH, but they're expressing the same thing. I'll say it one more time. A low pH means acidic, which is also a high pOH. A high pH is basic, but that's the same thing as saying a low pOH. Now, if you don't believe me that this is true, I'll show you a very simple way to to prove it to yourself, just take, for instance, this number here, the logarithm of a product 10 times 100. Well, we know a log, we know 100 times 10 is 1,000, so this is the same as saying log of 1,000. Well, what is the log of 1,000? Plug it into calculator, you get 1,000 log is 3. So that means 10 to the third power is 3. That's what that is. The log of a number is telling you what power of 10 you must raise it to give you 1,000. 10 to what power is 1,000? Well, I just showed you on that previous slide that the logarithm of a product is equal to the logarithm of the sum. It's the same thing. And this proves it. I can just split this up as the logarithm of 100 plus the logarithm of 10, which is the same. Logarithm of 100 is 2. 10 to the second power is 100. And 10 to the first power is 10. So 2 plus 1 is 3. 3 equals 3. It works out. So again, it's not expressed, but when you don't see a base written, but it's log, it's base 10. So log of 100 means what power of 10 do you have to raise it to get 100. So the log is just a different way of saying the exponent. Let's try a few more examples here just to show you how you do some pH calculations. So sometimes you'll be given information about the mass of a base or an acid in a certain volume of water. Let's say you're given 0.700 grams of sodium hydroxide in exactly 500 milliliters of water. What's the pH of that solution? Well, we're only going to stick with, in this class, to simple cases of really strong bases or really strong acids. So you can just assume that the acid and the base completely dissociate. So the moles of base that are present is equal to the moles of OH ions. Because ultimately, to get the pH of a solution, you have to know how many hydroxide ions are in the solution, which would then allow you to calculate how many H plus or protons are in the solution. So we've done calculations like this a lot. Converting grams to moles is pretty straightforward. You take the mass, divide it by the molar mass. Sodium hydroxide has a molar mass exactly equal to 40. I did this all in one step. You could do it in more than one step if you wanted to. 0.700 times 1 over 40 gives me a number, but the square brackets mean moles per liter. So this is moles, grams on top, cancel with grams on the bottom. Divided by volume, the volume is 500 milliliters, which is exactly 0.500 liters. When I do that, I get 0.0350 moles per liter. That's the hydroxide ion concentration. So how do I get the pH from that? I have two ways to attack it. I can go to my definition of Kw, which is always, remember, going to be true. The amount Kw always has this value. The product of this concentration times that concentration is always going to be equal to 10 to the negative 14th, right here. This is always true in any solution, in any aqueous solution. So I just calculated this number. So now I can calculate this because I know this is true. So that's what I'm doing here. I'm saying that that value of Kw equals the known, now calculated concentration of hydroxide times the unknown. And I solve for this by dividing this by that number. I just move the 0.0350 to the denominator. I get 2.9 to the negative 13. Let me just make sure that's right. 1 EE negative 14 divided by 0.0350, I get 2.9 times 10 to the negative 13th. So that is correct. And the pH of that solution, I would just say, you could have, I didn't need to round it off. I could have just kept it in my calculator, but I could also just write it, type it in 2.9, type it in again, 2.9 to the negative 13th. Now just take the logarithm of the number, log, you're going to get a negative number, but remember it's defined as the opposite of that with the negative sign there. So it's 12 point, what's that? So yeah, it shows you on that, 12.54. Why do I report it 12.54? Because I have two sig figs here. I need 2 decimal places there. So there's my answer. The other way I could have done that problem and got the same exact answer is this way. If I get the hydroxide ion concentration, I can then calculate the pOH by just plugging in the calculated concentration, 0.0350. That's my hydroxide, OH minus concentration. Press LOG. I take the opposite of it. I get 1.46, which is the pOH. I know that pOH and pH always add up to 14. I know this is always true. This is just another way of saying this. This is exactly the same as that. This is the logarithmic form of that. So whichever one you prefer to use doesn't matter to me. You'll get the same answer. So I know they add up to 14. If I know the pOH is 1.46, I just subtract that from 14 to get a pH of 12.54. That should make sense to you because the hydroxide ion concentration you calculated is a pretty large number. That's greater than 10 to the negative 7th moles per liter. Therefore, you are in a basic solution, and you should calculate a pH that's greater than 7, which I did. Another type of problem is, let's say you're given the pH of a solution. Let's say we measure the pH of seawater as 8.30. What are the concentration of protons and hydroxide ions in that solution? Just go to your definition of pH. pH is 8.3 is the negative log of H+. So my concentration of H+ is the inverse log of that negative 8.30, which I've written here. So on my calculator, I'd go in 8.3. You've seen this many times, so hopefully it's redundant at this point. I enter the negative like that, and I take second LOG, and I get what looks like a nice round number, but you have to put it in scientific notation. So I go to scientific notation, I see 5.0 times 10 to the negative 9th. Why did I write it like that again? You should know the answer by now. I have 2 decimal places in my pH value, so I have to have 2 significant figures in my concentration. And then if I know that, that's a number less than 10 to the negative 7th, so I know I must be in a basic solution, which I am. The pH is greater than 7, so that number is less than 10 to the negative 7th. And to get my OH, I can just divide the kW, 10 to the negative 14th, by that number I just calculated, and I get 2 to the negative 6th. Notice you can always check your work. The concentration of protons times the concentration of hydroxides must give you this number. And they do. 5 times 10 to the negative 9th times 2 to the negative 6th is 1 times 10 to the negative 14th. So you did it right. The other way to do this problem would be to take the original pH of the solution and subtract it from 14 to give you 5.70, but that's what the pOH is equal to. Therefore, the hydroxide ion concentration is just 10 to the opposite of that power, 10 to the negative 5.7, which does give you exactly the same answer. It must. So that's about as complicated as I want you to be able to do a pH problem. I don't think there are any sample problems in your textbook. They give you some calculations or some problems about what's called a titration reaction, which your lab this week will be covering. That's just dealing with molarity and mass and things like that. But specific problems like this, you're just going to have to watch this video to learn how to do them. And I'm going to give you some more homework problems as well after this next assignment is finished. Again, we're at 25 minutes. This is taking more videos than I thought, so this will finish up video number 3. Hopefully the last video we'll talk about just some different ways of how we actually measure these numbers using acid-base indicators and what's called a pH meter. And then I'll talk about buffers, which is a very important concept. It's not going to be mathematical, so that's the good news. We're just going to deal with strictly chemical explanation of it.